Hello everyone. In this video we are going to look at something that you have used and probably are familiar with in a general sense, but maybe you don't know the details of how it is done, and that is a JPEG image. So the JPEG image, that is the most common format in digital images, is made in 1992. It's a lossy compression, and by lossy means that when you compress it to a smaller size and you try to basically show it and reconstruct it back, so you encode it and then decode it. I'll talk about those. When you get the compressed version of the image, it has lower quality and you lose some data that you cannot get back. Okay, so if you save a higher quality image that has no loss in it, like directly from your digital camera, although digital cameras have loss in them too, but let's say high quality, and then you save that because it is like, I don't know, 100 megabytes or something, and you save it as a several hundred kilobytes or 1 meg JPEG image, you cannot do something to get that high quality image back if you get rid of it. So JPEG is coming from this group called Joint Photographic Experts Group, that they first developed this algorithm JPEG in 1992, and this is for digital images, as I said. So how would you convert an image to JPEG, right? And how would you bring down the size of the file, and where is it that you lose the information? So the first thing is you break down the image into 8 by 8 blocks, okay? So you break the image into smaller blocks that are 8 by 8. That's the first thing you do. And you also, the next thing you do is you make sure the values in this block are centered around 0. If m bits are used to store the values, then 2m-1 should be subtracted from them. What does that mean? It means, for instance, most of the images that you have are uint8, which means unsigned integer with 8 bits. That means the numbers for pixels are anywhere from 0 to what? 255. So m is 8 bits that you use to store those values. If that's the case, you see the numbers here are basically around 128. This is the average of the data, so which is 2 to the m-1. So now if I subtract this entire range minus 128, then you're gonna get from negative 128 to positive 127. Now the average of that is what? Is 0 instead of being what? Positive 128. Okay, so first you center it around 0. This is shown that it will lead to better and more efficient compression. So that's the first thing you do: extract the blocks, subtract, center them around 0. The next thing you do, you apply discrete cosine transform, DCT. Okay, and the discrete cosine transform, DCT, okay, let me add the words. So here I added the words in case you have not heard about this transformation. Is a transformation that you do to take your image into the frequency domain. So that is kind of similar to your fast Fourier transform, right? But with different basis functions. So the basis functions for it are these cosines, one for the x direction, one for the y direction. Okay, so the goal of this DCT, as I said, is to take your signal into the frequency domain now. So this is in the intensity domain so far. These are intensities, right? This is special information, intensities and special information. Here you get what? Here you get kind of like frequency contents. And why do you do that? I'll explain it in a second, but the goal of it is to take your signal to frequency domain and then apply the quantization and the lossy compression here. So as we'll see, the lossy compression, what happens, the compression here happens in this quantization, and in the encoder, right? But in this quantization is where you get the loss of the information because of a rounding operation and so on. But I'll explain why we don't directly encode the data in the intensity and special domain and we go to frequency domain. That's because of how our eyes are working. And I might make a separate video in the future and just explain the basics for discrete cosine transform. Okay, so my goal here in this video is not to maneuver a lot over this one, but as you can see, these two cosines have a frequency in them. You can see pi over m and pi over n, where m and n are the size of the pixels in the block. So in this case, they are both 8. Okay, and this is the formula for that transform here. Okay, and this constant alpha that you use for v and u direction, it is either 1 over square root m or a square root of 2 over m. This is for u of 0. These are for u of 1 all the way to 7 in this case, okay, because m, as I said, is 8. So this is the formula. The way that you can do it in MATLAB is by a simpler operation, and that is by matrix multiplication. So the way that you apply this t on the signal here, fxy is your image, okay? That is your 8 by 8 block. And TUV is the DCT cosine transform applied to the image in the U and V. So U and V are the x and y direction in the frequency domain, x and y are the special information. So the way you can do it, instead of applying this formula, you can pre-multiply the F signal, the F matrix, which is 8 by 8 block, by transpose of a matrix H, which this H is also 8 by 8 in this case, and post multiplied by 8. So you see H transform, right, F times H. And if you don't like this notation because that's a MATLAB notation, I can use what? I can use transform for you. So you can do H transform F times H. And what is H? Well, you can show that for 8 by 8. This is what? This is the H matrix, okay, which is basically coming from these two cosine functions, okay. Of course, one of them, not both of them, because you see here one of them is multiplied in one direction and the other one is multiplied in the other direction, right? So as you can see, like one of these and one of these you can consider like H transform, and the other one, right, plus this other cosine, you can consider H. So if you pre and post multiply, you can get your T, and the good thing about it is this H is constant, okay? So you get your frequency domain version of the signal, right? So as I said, the goal of the DCT is to take you to frequency domain. How? Let's take a look. So here, as I explained, the DC, and by the way, again, just to emphasize that the material here, including the code, are coming from digital image processing in MATLAB by Gonzalez, as well as a lot of material from Wikipedia, okay? So this is this is your what we call the basis functions, or two-dimensional basis functions for discrete cosine transform. So what DCT does is it transforms your block of input values, fx and y, to a linear combination of the 64 patterns. Here you see that you have these 64 small red windows, and each one of them has some pattern, okay? And if you basically filter, right, or transform your window by these 64 windows here, okay, so it's like basically doing a convolution here, something like a convolution here of that window and your 8 by 8, then this window and your 8 by 8, and so on. And what do they do? Well, if you look here, this is kind of like all over constant thing. So if I multiply or convolve my signal by 8 by 8, which is all constant and they are all the same, what would you get? Let's say all of these values are 1 over 64, right? If this is an 8 by 8 window, right? So this guy is an 8 by 8 window and all the values are what? 1 over 64. What are you doing with f of x, y? You're taking the average. You're adding all the elements of f, x, y and what? Dividing them by the total. So you get the average value of the signal, and that is what later we're going to call what? The DC coefficient. Okay? So the top left value in this TUV, the result of that, because this T is also 8 by 8, the top left corner element of that, which you're going to see, this guy here, that is your DC, that is the average of the signal, okay, which shows the overall, what, the average of the basic hue or the basic color of the signal. If it's intensity, that's the basic intensity of the signal. So it depends on whether we are doing it on a color image or we are doing it on a grayscale image, okay? That's the average intensity of the signal. That is your when this is 0 and 0. And what does it? How does it come from these cosines? Well, if you look here, I can explain that to you. Again, my goal is not to explain the entire cosine transform or something, but I think it's worth if we dig a little bit into it. So the top left corner is when u is 0 and what? V is 0. Okay? And when that happens, you clearly see that both of these become 0 and cosine of 0 is simply 1. Right? Yeah, and since u is 0, this is simply going to be square root of 1 over 8. Okay? And you get another one of that here, right, for v as well. So you get another one. So you basically get 1 over 8 here. And what it does is simply not doing anything because these cosines will have no frequency in them. But when you come here, let's say this window, what do you have? Here, if u is for this direction, right, and v is for this direction, then remember that this guy was u of 0, v of 0, right? But then this one, this is u of 2 and v of 0, right? So when that happens in the x direction, you do have a frequency. This u is 2, so now you have a frequency here, but in the v is still 0. So in the x direction, you have some oscillations, in the y direction not, and that's exactly what you see. You see, you're going from white to gray to black and then back to gray and then to white. So if you look at this profile from this direction, you can see what? You can see a cosine function, which is exactly this one here. Right? And as you go more into this direction, since the frequency of this first cosine is linearly proportional to u, right? You see here, as u goes up, this frequency goes up. You see that when you go in this direction, the frequency of oscillation gets bigger. The same thing happens in this direction where u is 0 in this direction and v is not. Let's say, for instance, this one here. Here, u is 0, but v is 5. And so now you have big frequency, big oscillations in the y direction. And finally, when you come here in the middle, let's say this one here, you have u equal v equal 6, so you have both variation in the x and y, right? So this captures both x and y frequencies, and you see oscillation happens in both of them. It's like this last one, which is 7 and 7, this is like a chessboard basically. Okay, so you can capture the frequencies in both directions. That's what this one does. So Just to give you a numerical example, if this is what? If this is f of x and y, so this is my f of x and y. If this is the patch of 8 by 8 block of image, the first thing I do, I subtract 128 from all of them, right? If I do that, then you see these pixels are anywhere from, I don't know, like 52 or something like that to maybe 154, right? So first thing I do is I subtract 128 from them, so they are centered around 0. So you see now I have 0, positive and negative values, right? Now in this case, specific in this case, you barely have positive values because most of the values are around or below 150 or 140. But that's not just this patch. The other blocks can have a lot of big numbers. They can have more white areas. So you first center it around 0, then you do this S transpose FH. So now this signal is what? This is your T of U and V. Okay? This is the frequency domain. Whereas you go from this direction to this direction, this direction all the way to the end, and this direction all the way to the end, you are increasing your frequencies. Now, let's take a look at this new matrix, this TU of V. What does it have? If you look, the important thing about it is the top left corner, which we called the DC component or the average component right here, or constant component. This one is quite larger than all other numbers. I mean, look at these numbers, 0.5, 4, 14, even 77. This guy is 400. So the DC value is way bigger than the other numbers, okay? Just keep that in mind. The rest of these 63 values here, we call them AC components or alternating components because each one of them corresponds to a U or a V that is non-zero. So each one of them is representing some frequency or two frequencies in general. Okay? Yeah? Now, as you can see, the bigger components in this matrix, the largest one is the top left corner. But also, if you can look at the rest of it, you can see that the part that has bigger values, the portion of this matrix that has the large values, is around here, something like this. It's this corner that has a lot bigger numbers compared to the rest of it. Or maybe you want to include this one as well. Okay? Yeah? Something like that. So the good thing about DCT is it captures the low frequencies, which are mostly the ones that we can see better. And here is the zero frequency DCT. It captures them on this top left corner of this result. Yes? So you can see here, I explained that it aggregates them all in one corner of this image. So now, what is the goal? The goal is if we can neglect this rest of these components that are small, can we just replace them with a bunch of zeros? So we basically only encode and put in memory this portion here that has the large numbers and get rid of these. Okay? Yeah, so capture the essence of the signal, the lower frequencies that our eyes can easily see, and get rid of what? The higher frequencies. Okay? Can we do that? And that is exactly what we want to do right now. So, the explanation is, as I said, our human eyes are good at seeing small differences in brightness over a large area, which means low frequencies. But they are not super good at going after what? High frequency brightness variations. When something changes very fast, our eyes cannot see that. If something moves very fast, our eyes cannot see that. And that's how the movies are made, right? They are basically a bunch of frames that are played at a frequency typically above 30 frames per second, although it's just a bunch of pictures back to back, but our eyes cannot see the basically the space between them, and to our eyes they look like a real movie. They look like they're moving, right? The objects are moving inside that. That's because our eyes cannot see high frequencies. So here, for that reason, these regions here that have high frequencies either in one direction or in both directions, we try to what? We try to convert to zero and get rid of them, and as I said, only encode the high frequencies. Let's see how we can do that. So the simple thing we can do is now, so far we have seen the DCT, right? How the DCT is working. Now the next step is what? Is to convert all of those numbers into something that we want to store. Okay, so that part is what we call normalization, and then what? Quantization. Okay, so this is the part that the high frequency components will be converted to zero, and the lower ones converted to something that the computer can easily store as a bunch of zeros and ones, and then we'll see how we do the final stage of the encoding. So now we're going to talk about normalization and quantization. So let's talk about that part. So what do we do next? Now we divide the signal TUV, which is this guy, as I just showed you, we divide it by a corresponding 8 by 8 matrix Z of U and V. So this division is element by element. Okay, in MATLAB it's like dot divide. We divide it by a window 8 by 8 where this Z has what in it? It has large values in the high frequency range. It has much larger values in high frequency range, but it has what? It has smaller values in the low frequency range. So what are we doing? When we are dividing by big numbers, we are literally what? By dividing these small numbers by a bunch of big numbers, we are making them even smaller. But these bigger numbers, if we divide them by smaller numbers, we are making them smaller, but not super small. Okay, you see? So here we are basically eliminating literally the small numbers by giving them more disadvantage and dividing them by bigger numbers. Okay, and to make sure that we are storing integers here, we have to quantize them, because when you divide these numbers by, like for instance 1.68 by 99, you get a number between 0 and 1, a small thing. Now here is the lossy part. We do the rounding operation. Now we do the rounding operation, and this is your what? This is the only lossy operation that you cannot get back. Once you convert, as I said, 1.68 over 99, which is almost something like, let's say, 0.65 or something. When you round it to 0, it's 0. It's gone. You cannot get this number back. That's where the loss is happening. Okay? You don't know what it was because you lost it. So here we get rid of some high frequencies. Now, and when you, as I said, round it, now you get something like this. So here is the matrix that we had from this patch. This was our fxy. We subtracted, we converted, we did DCT. Now we divide by ZUT and round it, and we get this. Now look, here you get you get a bunch of zeros. Look at them. All of these high frequency components, UV or both, now you get a lot of zeros, and you can get rid of these zeros. How? That's the next step, the encoding, the final encoding, the Hoffman encoding. But so far, you see, you got a lot of zeros, which you don't need to encode anymore. And that is the goal. So now it's kind of more like a sparse matrix, kind of, than this one here. Instead of storing this, now you want to store that. And at the same time, Getting rid of those are just high frequencies which our eyes might not be able to see well. Now let's talk about this well part of it. So what is that? One other thing I need to mention is in JPEG compression, there is one parameter that you can specify, and that is called the quality of the image, or the quality of the compression, and that is this parameter Q. This is like a scale factor that you can multiply all of the numbers in the Z matrix by. Okay, so this Q could be 10, 100, whatever, right? So you can have from 10% quality to 100 and so on. So this Q is like a scale factor. Okay, yes, it is like a scale factor. And if the quality of the image that you store is a low quality, then you are basically distorting a lot of these zeros to a lot of these small numbers to zero, so you get a lot more zeros. Okay, for a low quality image you get a lot more zeros, you're suppressing a lot more frequencies, and you get a lower quality. Okay, now I know those of you who are curious would ask me, how come when I get a bigger Q value, right, a higher quality, like 90% instead of 10%, how come I get basically smaller number of zeros, and if I use a smaller value for Q, I get bigger number of zeros? That doesn't make sense, because this Q is affecting Z, and Z is the denominator. So bigger Q or bigger quality means bigger Z means smaller T's or more zeros. The thing is, this Q here is between what? Between 0 and 1. Okay, this Q is between 0 and 1 here, not 0 to 100%. It's less than 1. Okay, so that's the reason the smaller Q is basically translating into more zeros. Okay, now talking about the quality, one of the things we have is most of the times for JPEG compression, we go with compressions of 10 to 1, up to 10 to 1, and up to 10 to 1 you might be very good. You can barely distinguish any changes from the original image to the compressed image. So although it goes down by a factor of 10 or more the size of the file, you are not going to be able to see any visible differences unless you zoom a lot. Okay, and you can go even as low as 100 by 1. You can bring down the size of the file 100 times. Now, of course, once you are more than 10, you can visibly, without zooming in, you can visibly see some distortions. So here, if you look at this image I got from Wikipedia, and you can look at any JPEG image, around the edges, you clearly see the pixelation. Okay, so you see the edges are not a smooth line or anything. There are several blocks of lines, and these are those compression artifacts, which many people call it what? Call it pixelation. So pixelation is very common in JPEG compression with very low quality, and in images that you see on the web, most of the images are JPEG because of the storage, and so most of the images are low quality like that. And the worst scenario is when the edges are contrasting edges. So they are between contrasting colors, like here, a dark and a bright, right? The background is bright, the object is dark, or vice versa. Those edges are very visible, these pixelations on them. Okay, very, very visible. And when they are curved also, when these edges are curved, because you don't have a straight line you can easily show. But once you get around the corner and you have a curve, you cannot show a curve by a bunch of square pixels. So now you see this band here. And in MPEG videos, right, which are like a similar thing for videos, right, then you can see a similar effect in MPEG videos, and that is what we call a mosquito noise. Okay, So it's like a lot of small mosquitoes are here around what? Around that edge. As the movie is being played, you see that edge on the person's shirt or something. It has like a swarm of these small mosquitoes around it, and it is moving with the person. Okay, so although it's very good for compression, you have to know your limitations of quality as well. You don't want a huge distortion. Okay, so now that I explained this normalization and quantization step, it is time to what? Talk about the final encoding stage. Okay, how is that one going to be done? The way that we do it is with Huffman encoding and what we call also run length encoding, which are methods of entropy encoding. And entropy encoding is a topic of its own or several lectures, and that is generally based on the idea of the frequency of something happening. Okay, so if something is happening less frequent or more frequent, you give them a variable size of bits, a variable number of bits to be stored. The less frequent they are, the more number of bits you need to store them. The more frequent, the less number of bits. Okay, so that is the overall idea of entropy coding. And the good thing about it is it's a lossless lossless encoding and compression. So this last stage of JPEG, there is no loss here. This is the lossy part. This is lossless. Okay, now let's see how it is done for JPEG. So the way that you do it is, remember, this is my result so far. This guy down here, this one is the final what? This guy is the final result as of now. Now I want to store these values, and what I really care about are these numbers, as I said, these non-zero ones. These are the numbers that I want to store. But as you can see, if I want to say, in order to store them, I store this block, the problem is now you're storing a bunch of extra zeros. And you don't want to store those zeros. You just want to store these non-zero numbers. So storing a block that involves all the non-zeros could not be the best. And sometimes you might get a non-zero number here. You might get a 1 here. And if there is a 1 here because of some noise or something, then there is a good chance that what? Now you have to store a huge number of pixels, many of them 0. So here you want to do a nicer way to do it. And to do that, we go back and look at the frequency contents. So if you look at the matrix here of these patterns, you can see that, let me use a marker that is quite visible on this, I guess maybe a blue is good on this, a thick one. So if you look at this, and if you look at the mirror image of that with respect to the main diagonal, you see that these two are basically storing the same information. The same frequency, just in two different directions, but the frequency these two are storing is the same. And also this one and this one also kind of the same thing. This one is kind of like related to those two, right? But the frequency content of it is split between the two directions. So a way to go about it is, instead of storing that whole thing, we choose a pattern, and here I did a little bit cleanup so I can draw over it for you. So what you'll do is you start storing these values with a pattern and not go in a square. So I start at this number here at this DC frequency, and then instead of going, as I said, in a square, I try to go something like this and get those mirrored elements or so. Okay, so this is kind of like storing an upper triangular here, right? And I stop once I get to a bunch of zeros, so I don't need to go any further. So this way, by this pattern, this zigzag pattern, I can do a lot more efficient encoding, and that is exactly what we are doing here. This matrix that you can see is the matrix of the scan pattern. So you start at the DC top left corner, and then you go to pixel 1, which is the second to the second pixel on the first row. Then you go to the 2, you see 1 and 2, they have the same frequency. Then you go down to 3, then you go down to 4 and 5, and you see that pattern is shown here. Okay, and you can what? As I mentioned here, you can group similar frequencies together, right? So that is what you're doing here. If you do that on this transform image and scale down and normalized image, you'll get this, right? So you see now I picked on that triangle here. I picked on that triangle and I kind of rotated 45 degrees. So now I get this guy. With that zigzag scan, I get this one. And now the ones that I want, those pixels, those not the values that are I want are right up here. So now I can go about those. Okay, now how do I put these numbers? How do I store them? This is the part that we say run length encoding. Okay, so what is the run length encoding? This is this part. Let's explain. The way you do it is you use 2 8 bits, so you have 8 bits here and you have 8 bits there, and the first 8 bits you basically break it into 2 4 bits. The first 4 bits you use to store something called run length. The second 4 bits you use to store something called size, and the last 8 bits are what you store the amplitude. Okay, so what are these 3 variables? So if x is your non-zero quantized AC coefficient, so basically any of these numbers, any of these, not that one, not that one, the rest of them, all of these AC components, all of these. If x is one of these, then the way you store it is what? The first thing you need, you see, so it has to be the AC component, it has to be quantized non-zero coefficient. The first number is run length, which is the number of zeros that came before this AC coefficient. For instance, if I want to store what? If I want to store this -3, when I go down in this triangle, how many zeros do I see before this -3? Nothing. Right above it, there is no zero. So no zero came before this -3, so the run length for it, for this first number, is what? 0. Size is the number of bits you require to store x. Well, the number is 3. 3 can be written as a 1 and 1 in binary, right? So you really need what? Basically 2 bits to store the magnitude of what? The magnitude of 3. And that is what you can see here. That 0 is the run length. This 2 is that magnitude, the number of bits that you need to show the size of it. And finally, the amplitude is the bit representation of x. So here, whatever it is, right? -3, which is really, as I said, 1 and 1. Of course, you need something for that negative as well. But this is basically, this first part is just for that number 3. Now, if I look at the other -3 down here, look at this one. This one, is there any 0 preceding it, before it? Yes. Because once I come down, there is this 0 right above this -3 in blue. So there is 1 0 behind it. That's why, if you look, there is a 1 here. And again, you need 2 bits to store it, and the value is -3. Do you see that? Yeah? Okay. So this is how you can store that. And now if you look at this -2 here, that -2, you see there is 1 that you can store it with, but there is a 0 here. Why 0? So in this method, if that information is stored in a previous bit, it's not going to be stored again, right? So since this -3 already mentioned that I had a 0 behind me, then the next value after that, -2, does not need to say, hey, I had a 0, another 0 behind me, because it's gonna repeat this 1, right? So this one is gonna have 1, the next one is gonna have 1, they're gonna all have 1 until they see another 0. So once one of them refers to it, that's it. The rest of them, they do not need to do that. You can see a similar thing here. Look at this -1. It has 5 zeros behind it, so you see that here, right? But the next -1 after that, it does not need to also say again, hey, I had another 5 zeros behind me. So for this second one, you see what? You see there is a 0. Okay, so you only refer to those number of zeros before that, that run length, you just use it what? You just mention it or store it once. Store it only for, or store it only once. Okay, for one of the numbers. And afterwards you don't. Okay, so you get this one, right? Let's do a little bit clean up. So you get that, and now you get this final thing here. This is what we call the run length encoding, right? And finally, use what? Use the Huffman coding on the rest of it. So once you have this, then you apply one final Huffman coding. And Huffman coding, I am going to make a video on it, so you get the table here, right? And I'm going to make a video and explain the Huffman coding for you, right? So that needs a lecture of its own if I want to explain the Huffman coding. And I'm gonna do that, but here, this is your final product. This is the final thing that will be encoded, and here we refer to it as what? As the compressed image or the encoded image. Now, you cannot show that, so that's not what you are saving. When you save an image, a PNG image or some other lossless compression format, when you save it as JPEG, you are not saving this. This is just the encoded version of the image. Okay, this is a very small. It's a table. It's a bunch of numbers, right? If you want to see the saved version of the image or the real compressed version of the image, you have to go back. Okay, so this is not your final save thing. You need to go back. So you need to get that compressed code. You need to decode it, right? So you need to basically undo that Huffman encoding and running length encoding and the zigzag pattern. Then you denormalize it. So basically, instead of dividing by the Z signal here, now you multiply by the Z, and then you apply inverse. So here you get basically the T, and then you apply inverse the discrete cosine transform to get what? To get that F. Now, not that original F, a compressed, basically reconstructed version of the image that has smaller volume. It needs a smaller storage, but clearly it has a lower quality compared to F. This is an approximation of F. And then once you get all these blocks, you use a merger, you combine them together to get your what? Reconstruction image. So this whole set of operations that we did, we call it decoding, and all of the ones that we did here on the top, we call them what? We call them encoding. So this is encoding the image into the Huffman using Huffman finally. And here is what, as I said, this bottom part is the decoding part. Okay, this is what you're going to save. A few other things that I need to explain before we go and look at the code. So a couple of other things I need to explain for you. One of them is when you use this run length method and size, remember you store them on the same bytes. Each one of them gets 4 bits, okay? What does it mean? It means that only, since each one of them will get only 4 bits, and with 4 bits you can only store numbers from 0 to 15, right? Because the maximum number you have is 1, 1, 1, 1 in a binary, which is 15. The smallest one is 0, 0, 0, 0 in the base of 2, which is what? Which is 0. So it can go at most up to 15. So for the run length, which is showing the preceding zeros, you can only show how many preceding zeros? Only 15 of them before a non-zero AC coefficient. Only you can have up to 15 of that. So if there is, let's say, a 1 here, if there is a 1 here, the number of zeros before that, as you can see here, look, 6 and 5, that's 11, plus 6, that's 17, 17 plus 7, that's 24, 24 and 32, 34. So that one, the run length is 34, but I can at most show 15. So what can I do here? If a 1 appears, a non-zero AC value appears after more than 15 zeros, how can I handle this scenario, right? The way to store it is using this special thing like this. If you see some of these triplets is stored at 1500, that means there were more than 15 zeros before that, okay? And we had to store it like that. And the other thing that is important is what we call end of block, or EOB. What is that one? This is for when the sequence is ending prematurely when the remaining coefficients are 0, okay? So if there is no 1 like that and the rest of it is all 0, like in this case, you see at here, that's it. The rest of it is all zeros. So here I have to say that right after that at this location, not that negative one, that negative one is still a non-zero. Right here is the end of block. This is where that after it there is nothing, there is just 0, and I don't need to store those numbers anymore. So at the very end of it, I say what? 0, 0. 0, 0 without a third number. That simply means what? As you can see, it means end of block. And that exactly is corresponding to that value over there. Okay, so you need to have something that checks for end of block and make sure that after that you're not storing anything. Okay, so this is one thing, this end of block that you see also in the code and in JPEG algorithm. I wanted to explain that, and there is one other thing I wanted to explain, and that is that the discrete cosine transform that we applied, right, and we went from basically this to this to this. What it does, if you look at the numbers, here all of these numbers are between 0 to 255, but if you look at these guys, they have what? They have a decimal and two extra decimals, the numbers after the decimal point. So if these guys I can store with 8 bits, these guys I cannot simply store with 8 bits. These guys need more than 8 bits to be able to store them, and the way that they are stored, we need up to 11 bits or more sometimes, or more bits to store them. So this is bigger than or equal what? 11 bits to store them. But this is a temporary thing and it's for a small block really. Therefore, you really are not going to lose the efficiency in this algorithm. Still, this method is going to save you a lot of volume and storage. So now let's go and look at the code. So here I'm going to upload a zipped folder for you and give you the download link for a zipped folder, because this JPEG and encoding and decoding it needs a bunch of utility files. One is Huff to Matt, one is Huffman, and the other one is Matt to Huff, and the other one is Unravel, which is written as really in C, and then using MEX, it is incorporated into MATLAB. So here you have MEX files, and here is my script, the test script, JPEG text. I grab the image Lena, and I read the image Lena, and then I store it at a quality of 25%. You see this number is between 0 to 1. And the file here, the function that stores the JPEG, IM to JPEG, it needs your image, which is a grayscale image. It needs the quality, which is between 0 and 1, and it needs the number of bits. Here, these images are all 8 bits. So the way that I call it is image quality and 8, and this gives me Y, which is the encoded what, which is the encoded value. So if you look at this Y is not an image, okay? This image to JPEG, the output of it is a structure, which is the end result here. This is your Y, and this is not something you can display, okay? This is the Huffman coding result. So when I run this, if you look at Y, this Y is a structure that has a size of 512 by 512, 8, 40, 96, 25, and 1 by 1 Huffman, right? So you can say Y dot Huffman, and you can see basically here is that histogram and the code that is used in Huffman encoding. Okay, as I said, I'm going to make a video on Huffman encoding and explain that in more detail. So if you want the reconstructed image, if you want this one, if you want this, right, the final image F hat, the reconstructed one, compressed one, you have to use the other function, JPEG to image. And here I'm going to apply the JPEG decompressed image, right? So it decodes the compressed image Y, generating the reconstruction approximated X. So I get that Y, I pass it to JPEG to image, I get the image compressed, and I also show you the image compressed. The other thing I do at the end of this code, I write that image compressed to this JPEG file called lena.compressed, _compressed. And I want you to see the size difference between original Lena and what? The compressed Lena. So here we go and run it, and we see them side by side, okay? You see, there is barely anything you can visually distinguish between this one and this one. Although this image I got myself was JPEG, I saved it as a ping. It's not really a ping. I did a little bit of cheating, to be honest here, because I did not have a very good high quality Lena. If you look at this, this is JPEG itself, okay? You can clearly see this is a 512 by 512 image, and clearly this is not high quality. And if you look here again, you can see the distortion as well. There is barely too much of a thing to see and distinguish between them. So they are very similar, but if you do it with a high quality image also, up to 10% quality, up to 0.1, it's very hard to distinguish unless you zoom in big time. Now, the thing that I wanted to show you is this. Now, if you look at the original Lena that I read in, and if you look at the Lena compressed, look at the size difference. 463 kilobyte versus 37. Do you see how much of size reduction you can get by JPEG compression? Okay, so JPEG compression can really saves you a lot of space, and this is the beauty of JPEG compression. As long as this number is, as I said, more than 0.1, you probably get a relatively good image and save a lot of storage. So I'm gonna put everything, as I said, in the zip folder and let you download it under the video description. One last thing, I mentioned that this code, none of these two code is mine or any of those. The only thing I wrote was this test script. Okay, the code is basically written under a toolbox, okay, which you can download under GitHub. It's called DIPUM, right? It's a digital image processing toolbox, and it is basically these are the functions that you can see at the end of the book, Digital Image Processing by Gonzalez. So none of these functions are written by me, and I don't claim any credit on them. So hopefully you learned some basics about JPEG compression and the details behind the scene, how it is work and how it can help you. Thank you so much for your attention. I'll see you in the next video.